recording. So, the last, maybe last thing, almost the last thing from SQL is that we have views, and view is a query that we store essentially as a string. Just select something and something, just stored as a string, not as a data subset. That's completely different beast called materialized view. Materialized view is a definition of the query, but the query will be executed immediately upon definition, and then will be rebuilt. In most cases incrementally. So system will try to update it incrementally when base table changes. So just a view, that's just a macros. So it's just a program that will be eventually executed when you try to select data from it. So view look for end user or for a person who has possibility to run SQL queries, looks like any other table. But instead of reading data from base table, reading data from a view lead to reading data from base table, but invisibly. So user contacts with view, and view essentially perform join. But from the point of view of user, it just select from single table. And there is no such thing of that table, and that table is built on the fly using supplied in view definition query. So we may say create view test view as some selection, and that means that all the people who have access to test view and don't have access to tests may see only the facts that the student somehow tested by this professor for this lecture, and grades are private marks. So grades is private data. You can't see it. So if I have access to table, then I may extract everything. But in this case, I have a read access to this view. I can't do anything but just to see only these three columns. So views may serve for privacy. If I restrict access to base table and provide access to views, and or it may simplify queries instead of repeating common complex joins like student join attends, join lecture, join professor with conditions. Every time I need to find something, I may create view that collects everything, and that view looks like student name, semester, title, and professor, lecture title, and professor name, and that's all. Not in form of IDs, but in form of student name, semester, title, and professor name. And then I may, let's say, select distinct semesters from this professor's name, Socrates. And so for me, then this view looks like table. I may use it in from easily, but this view, this selection will be executed. So join is hard work. To join tables is hard work and long, and it took long time. And it will be done, actual joining, only when I ask for it here, and not at the moment of your creation, and not regularly, and not upon base table changes. Classical views don't change, don't store materialized. It's materialized contents. And if I say create materialized view, then it's much more complex and almost substantially different beast. So views may be used for views may be used to implement is-A relationships. I have a table of employee with some data, and then professor's data, and then assistant data. And then I create a view of professor that combine. So in base tables, in real tables, I have either relationships stored in multiple tables. And that's good for normalization. We'll look today, and for other things. Sorry. I'm sorry. So tables are good, and views are useful to select. So essentially, subtypes implemented as a view. Professor is a result of join of professor's data with employee and has all the fields. So professor data has no name, for example, and a professor table do have name field. So we may implement subtypes as a view, or vice versa, store data in tables, and then implement employee supertype of employee implement as a view. So employee is all the people who are professors and all the people who are assistants and all other employees, and union and union and union. That's different way. So views may hide something, may hide complexity of queries, hide columns or values, and allow to implement differently hierarchies. Some views may be updatable. If a view contains some calculations, that's probably not updatable. If my view is like this, and it contains average, and I try to update this this like table, setting a value here, that doesn't mean how I don't know how to change it. This person may have multiple records, and average is just calculation. So where to change? So new average become correct. But if I have a view, and it's the same thing if I have a view of joins, in most cases, that's not possible to change. But if a view of this kind, and I change, let's say, person number, why not? So it's a cell in record in a base table is unique for each record. So if base tables records can be tracked uniquely for records of values, for values from view results, then view is updatable. And there are some select person. So some views may be updatable, and some views may not be updatable. So all the views and SQL view is updatable. So in theory, some views may be updatable, but SQL don't permit it. So SQL places some restrictions on updating views, and don't try to check that's really possible in this situation. So if the view involves only single base relation, then SQL view is updatable. And view involves the key, contains the key. So if I skip the key and I just extract other fields, then I can't identify exactly that record. So primary key should be selected for that relation, and view doesn't involve aggregations, group bys, distinct. So no joins, no group bys, no distincts, no aggregates, and key should be present. Then view is updatable in SQL. But in many cases, some other views may be updatable, not only not only single base, and result of joins may be updatable too. So we can trace for if I change. So let's say I want to change this result of lecture view, title, CP, and name. And each time I see title, CP, and name, that's from single lecture with a title and for single professor. So if I change CP, let's say, then it may go to, I may find record in the lecture where it comes from. Go to this record and change it. So essentially, this view may be updatable, just points of this point updates. But to insert, I have not enough records, not enough data, as I have no lecture IDs, professor IDs. So if I try to insert a record, that's not possible. So views may be updatable for some individual updates and not updatable for others. SQL view is updatable totally. If SQL permits view updates, then you may change anything. You may insert data, and key allows for it, and so on. So, and let's keep triggers, as triggers is a special thing, and move to other topic. Other topic that's called, let's look. It's called normalization. Oh, here. It is called normalization. So the question is normalization. Normalization is a main part of relational design theory. So how to do three things. First thing is, I have a database. I have a schema, so a couple of tables. Let's design somehow, maybe using ER first, maybe not, maybe just a bunch of create tables and create tables with constraints and so on. But how to assess the quality? Is it good database or not? Is it a good couple of tables or not? Or maybe that's better than this, so or vice versa. So if I have some schemas, how to compare them, or how to compare, or how to assess them in this absolute, some absolute, not numbers, but on some scale maybe. So normal forms are like quality seals, so or quality marks. So normal forms from 1 to 4th plus Boy's code normal form plus domain key normal form plus 5th normal form, 6th normal form, and even 7th. But at the practice, in most most projects stop at either Boy's code normal form or 3rd normal form. So we look at all of them, but we need to have this idea that we don't need to go too deep. And yes, there are some methodologies, and not very widespread, but still quite popular, like anchor modeling. And anchor modeling is a methodology for building incrementally designed data warehouses. And database is a common term, so just a storage for your data. And data warehouse is a special kind of database that's aimed for long storing of historical data and providing providing some querying to make decisions. So decision support, so-called decision support system. And data warehouse is a much bigger database structured a little bit differently. And if I have my database of mine, of my project, then I may change it as I want. I may add columns, change tables, remove tables, create new tables, and do something. In subsequent versions of my product, I may change databases as I want. But in a data warehouse, we need to design it upfront and create tables to store data maybe for decades, for tens of years in future. So, and if we need to change something that may break too many things or many decision support systems that works with it, so we are not allowed to change something, or that's possible, but it's quite hard due to dependencies. So anchor modeling is a methodology, quite recent methodology, how to design data warehouses in such a way that we don't need to change anything that we already created. So all the tables created will not change their structure at all. No reason to change them. And just new tables and new tables and new tables, we may introduce changes in form of new tables, of additional tables. And that leads to many useful things. So our data warehouse may work without maintenance at all. So if I want to change a table, then I need essentially stop querying this table at least. And in many cases, I need to migrate data to create another table and to migrate data between them. So idea that normal form number six normal form is the basis of that methodology of anchor modeling. That's very useful for data warehouse. So in transactional processing systems, that just keeping orders, keeping an eye on finances, on delivery, on production, and current things, messages, and so on. Probably we don't need deep normalization, but in other places, deep normalization is good. And every normal form means that database is somehow safe. So that's a mark of safety or quality. So we may not expect, so database is free from some risks called anomalies, and we'll look at that. Second thing in relational design theory, beside normal form, are just definition. We can check. I have a tables, I have a schema, and I have some dependencies or descriptions of what's possible and what's not possible with our data. And then I go to the schema, you get the schema and check it and say, oh, I see that schema is in first normal or in second or in third. So I can assess it. And that's just assessment on checking some conditions. And then I can improve if thinking higher normal forms being better, then I can improve the quality of schema. And there is a synthesis algorithm that's based on the composition algorithm, how to make our normal form, how to make schema to convert it to a higher normal form. And the last thing is how to construct it, not just improve, but I have no schema at hand, and how to start with such called universal relation, just single table, and how to move to normal form that I want. So normal forms in first place deal with redundancy, and redundancy, so duplicates in some notion of redundancy is duplicates, but in some cases those duplicates are just real replicas. Yes, I have just record and another record that's completely the same. But in some cases, that's not so not only just multiple copies of the data. It may be like a redundancy in this form that I have, let's say, order contents, order items. I have order that consists of bread, milk, and juice. And bread costs 10 something, milk costs 12, and juice costs 8. So total is 30. And so I have just 3 records, 10, 12, and 8. And different table with order header. So that's a table of order items, and different table of orders or order headers that has just single record for the whole order, telling who is ordered, delivery address, total cost, and date of order and date of delivery and total cost. And it may happen that here, if I calculate total, just summing values, I have 30, and by some occasion, that's just completely different record, and it can be manually manipulated by people or by error or something. And their total cost of that order is, let's say, 40 or 20 or something else. So I have essentially that's redundancy. I'm redundantly that storage of that total cost is redundant, and that redundancy leads to inconsistency. If I calculate here, I have one number, I have one result. If I calculate, get data from here, I have completely different result. And in some cases, I can check, but I don't know where error is. It may happen that error not in that I calculated wrongly this total. Total was calculated right, and so number of 40 is correct, but some bad person deleted order item. So right version of data, what's right is not so evident. In some cases, yes, that may be some data is more basic. So I just recalculated, and total cost is essentially a cached value. So I've just not invalidated my cache. And the only problem, I need to just invalidate it. But in some cases, I have just different results calculated by different ways. I don't know who to trust, which result to trust. So that's a problem of redundancy. Not just a waste of storage space, and in modern times, storage space of terabytes costs not nothing, but quite small for companies. And 1 terabyte of storage in physical things costs tens of dollars, and terabyte is quite big space. So even to keep company data, if I try to keep all the data from video surveillance, yes, from video cameras, yes, it would be a waste probably. But we're speaking about databases and not storage of raw data and raw video. So for databases, waste of storage space is for decades already. It's not main reason, not main reason of normalization. That's not a problem. But and yes, importance is diminishing as storage gets cheaper, and this density will ever increase, and so on. So storage space is cheap. But problem is that we have not consistent data, and we need to perform additional work to do multiple updates in different places. When event happens that change, and we need to accommodate this event and change here and there and there and there and there. And it may happen that we just forgot about some place when we need to change, or failed to do so, or something. So additional work to keep multiple copies of data consistent, and additional code. That logic of multiple updaters need to be implemented by some people. And so we have a risk of people, programmers, errors. So I just forgot that I need to update accordingly that table. Or I have millions of tables. Why do you blame me for I didn't change one of the million of tables? So problems are here. Problems is with data consistency. So let's look at anomalies. Anomalies in classical anomalies, we have three anomalies, three kinds of anomalies, called update anomaly, insert anomaly, and delete anomaly, respectively. So if I have just this table is called universal relation. That's a table, maybe come from paper journal, paper not notebook, but table book. So and yes, journal. So I have a paper thing, open it, graph it, draw lines, draw table, and then fill it. That Socrates is he has a professor number of this, his level of that, his room of that is assigned to deliver a lecture on ethics, and lecture number is this, and points are that. So, and then if Socrates will teach my ethics, we need to fill the line with all the data about Socrates and all the data about my ethics. If someone else, so for each and that table called professors and lectures. What's bad with this schema? That's quite good schema to read. And non-normalized, that's non-normalized schema. And non-normalized schemas are very good to read. We don't need to join anything. We just have everything at hand in single table. If I want to find all the lectures delivered by Socrates, I can do it easily, and so on. So non-normalized schemas for reading is the best. But what are anomalies? What happens when Socrates assigned a different room or moves to a different room? I need to go to every record and change room from this number to different number. And all the records should be changed in single operation. And I wanted to, I preferred this operation happens atomically. That's one thing. So to define this thing. Second, and why is this a problem? Problem is that in most cases in relational databases, when we work with a table, if I have a table for professor, distinct table of professor, and that professor changed the place, changed the room, that's just single fact. Why do I need to reflect that fact in multiple records and in as many records as that professor read lectures, and maybe that professor teach students, or maybe something else? What's the connection? Why a changing of simple fact need to be reflected here and there and there and there, and that may lead to inconsistency. I may forgot to change somewhere, or just trying to change and somewhere I have an error or failure. So, and my table may finish in inconsistent state. In some places, Socrates has room of this number, and in other records, tell me that Socrates in another room. So, and who to trust, I don't know. That's update anomaly. Update anomaly is situation when to update single fact, I need to change multiple records. Insert anomaly. What happens if some person, Baseman, is elected as a new professor? I can't add that professor that teach nothing, that teach no lectures to this table. I need to fill everything. When you teach something, please come later. When you will teach something. So I need to, I can put a line, put a record in this table only when everything is defined. Yes, Baseman is a professor, room is this, person number is that, but oh, no lecture, I can't write. So that's insert anomaly. I can't insert data if I have no why, but why? So professor is elected. Why I can't store information about it, about this fact? So that's it. And delete anomaly is the same thing. If Popper doesn't teach this semester, in this semester will not teach, so we need to remove information of connection Popper to their Wiener Kreis. But we can remove only this lecturer information and Popper and professor information together. So delete anomaly is about deletes when factual when we need to remove just fact portion of effect, part of effect, but we need to remove the whole record, and then we'll lose information about other part. So that two other kinds of anomalies of problems is universal table, universal relation. In some cases, we want to some other way besides normalization. That's using multi-version databases, how to solve these problems. As storage becomes cheaper, we never throw anything away. And in many cases, that's more expensive to think about what to keep than simply to keep everything. That's not in databases, that's called data lake. And data lake is a big storage of everything that we have a grasp. And then we store all the facts, we never delete. So if fact is in our system, then we don't want to delete, we'll keep it as some former version. We'll just maybe set a status flag or some flag to delete it or something. In this case, we have no delete anomalies. We don't delete anything. We just mark a record that it's deleted. But all the data is present, and if we need, we can get it. Second consequence, we perform no update in place. If we want to change something, we leave previous record, mark it maybe as, or instead of delete, we may just have a timestamp or two timestamps of data validity interval, and that's all. So when we want to update something, we create new version of record, change it there. So we have no update anomalies. We never change old versions. So all the tuples remains the same, and each tuple is connected with some time interval, and we know that Socrates had a room of 226 from 1st March 1st of 2004 to 7th of November of 2009. Okay, and now it lives there. So we have no update anomalies in this case. In multi-version databases, insert anomalies still exist if I need to have a full data set to full data fields values set to insert a record, but that's not a big problem. We just put null values where we don't know something, and that leads to no inconsistencies. So that's not good situation, but that's not a big problem. And no SQL movement is mostly partially for denormalization, for data denormalization. That's another some solution for the same thing. Not solution. We can put restriction differently. We can use XML schemas. We can use completely different tools to store data and to struggle with anomalies, with these problems completely differently. But in relational databases, we solve it in a special way. How? Let me, I'm sorry, just one moment. Just one moment. So main notion in normalization theory is a functional dependency, and functional dependency source is not a data. Functional dependency source is requirements, is functional requirements. So requirements that set you a task, what you need to solve. So as a developer, as architect or analyst, you need to go to your customer and ask for, you may not call it functional dependencies, but you need to understand what you need to know. So what's it? I have a schema for a single table. Table R has 4 columns, A, B, C, and D. This respective domains. Domain for A, domain for B, domain for C, and domain for D. Domain is just a set of possible values or just data type. Integer, string, dates, and so on. And R, so R Greek, or not Greek, what's called Gothic letter. So Greek letter is for just header, and just big letter R of this kind is for body of this table of this relation. Let's A, Greek A and Greek alpha and Greek beta is a subset of columns. So R, Gothic R is a set. So A is a subset. So not A. Alpha may be A and B, or B and C, or just D, or or the whole R. So that's that's a subset that may be equal to the whole set. So A alpha is just a set of columns, and beta is set of columns too. They may be the same columns, but probably they're different. And we may say that alpha, that beta functionally depends on A or on alpha. So there is a functional dependency from alpha to beta, if and only if for every possible values, for every possible R and S, and R is a record, S is a record, as R here, R small r and small s, belongs to big R, and R is a table of records. So elements of this set are records, consist of tuples, tuples. So if for every possible pair, this this qualification, also qualification, not existent for each pair of R and S that are records from this table, if alpha and in first record and is exactly the same as alpha columns in second record, then betas are the same. So there is a function. That's why it's called functional dependency. From all the combinations of domains for alpha, from Cartesian product of all the domains, there is a function into in the Cartesian product of all the domains for beta. So let's look at small table and just check. Is this hold or not? I have a table and I try to check that. Let's suppose that there is a functional dependency from A to B. Let's check. First record and second record for every pair. So we need to compare all the pairs. If alpha equals to alpha, so A equals to B, A4, oh, A4 equals to A1. Oh, they are not equal. So we don't need to follow this. Completely forgot all mathematics terminology. Follows. Follows or implicate. So in math, that's called implication. So left side of implication is false. So right side may be or not be true. So okay, A4 is not equal to A1. A4 is not equal to A1. A4 is not equal to A2. A4 is not equal to A3. So nothing follows from these pairs. And then A1 and A1. Oh, we have an equality. So A1 and A1 in two different records. So this column is the same in two different records. So we need to check that right side records are the same too. B1 and B1. Great. Okay. But we just checked. And what if they will be different? If we can find at least single contradiction, so A1 and A1 here, and B1 and B10 there. Oh, that's not functional. So that means that every time when A has a value of A1, B has the same value, B1. And here A1 and B10, oh, they're different. So there is no function. So having data at hand, we can check that functional dependency doesn't hold. We can check contradiction just by finding just single examples that contradicts this definition. But here at this step, that's okay. But we need to compare everything. A1 to A1 is B1, A2, and now I understand what I search for. I search for groups with the same A, the same value for A. But as I can see, A4, A2 is single record, A2 is single record, A3 is single record, and only A1 is a pair. Oh, no more. So essentially, we compared all the pairs. And some pairs are just different values, so it leads to no further checks. But only one pair we checked, and it's good. So A is really, we checked that functional dependency B from A does hold. So there is a functional dependency from A to B. So let's check another. Alpha and beta may be not only single columns, they may be groups of columns, sets of columns. C and D. Let's check. So we need to find combinations. C4 and D3, C1 and D1, they're different. C1 and D2, third combination. C3 and D4, another combination. So no repeating combination. C4 and O is the same. C4 is and C4, D3 and D3. So we need to find pairs of values that are pairs of records with all the values, all the pairs of values that are the same. So we need to check what's with B. Oh, B2 and B2. Great. So this pair of records doesn't contradict to functional dependency. And all other records are just different, have just different values. So yes, CD follows B. B depends on CD. Does hold. That's good. So we've found no contradictory data. In case when all the combinations of CD are different, we don't need to check anything. Yes, So every time we see some combination of C and D, then B is something. But all the combinations of C and D is only in single record, and then B is have just single value anyway. But let's check B to C. B2, B1, different. Okay, B1 and B1. C1 and C1, great. So no contradictions. B2 and B2, C4 and C3, contradiction. We don't need to check anything else. And even in first and last records, they are the same. So we can't say that we have a function from B to C. Sometimes when we have B2, C is C4, and sometimes C3. That's not a function. Function has just unique value for each argument. By definition of function. So B to C is not a functional dependency. And we may check something else. Let's say from D to C, D3 and D3, C4 and C4. Okay, D1, just single record, don't check. D2 and D2, C1 and C3, different. So D to C is not a functional dependency. So we may check for all the every possible combinations. Let's say B and D follows A. B2 and D3, B2 and D3, A3, A4 and D3, different. So that's not. So having a table, having a data, we may check something for functional dependency and don't prove it. We can check a functional dependency. Let's see, violation. As I see this table and check everything and come and say, oh, we have a functional dependency of from A to B. You may check A1 and B1, A1 and B1, A, so great. But that if that solution comes, that decision come from data, not from something from customer. If customers say every time when A, B should be unique. In our business, that's it. So that's the situation in our business. Every time we create an order has unique ID and unique manager assigned to it. So A is the order ID and B is a manager. And they say that in our business, single manager performs all the tasks by order. So they say, and we need to follow. But in some other business, they may say, oh, we may assign multiple managers for the same order, so we have no such functional dependency. We have no such dependency. So if I find something in data, that doesn't mean that functional dependency really holds. The only source of truth is requirements from customer. That's just current situation. I check this, and then user, I created a database, I created an application, deliver it, ship it, and customer began to use it, and then user of a customer using my application, putting data inside, and then I see, oh, strange, he added to this table A1, B10 in new record. Why? I think that I have a functional dependency. I've seen this data. You break me, you break my application. That's your fault. No, that's yours fault. You think that this is all the data that's possible. No, it isn't. Users may add some data. So restrictions are in business, not in programming. Restrictions come from business. And if they can add A1 and B10, you just, so your source data was not full, yes, but we can't provide you all the possible data for this table. So, and that would be your fault. So never never use table data to prove functional dependencies that can't be proved by data. That can only, using data, you can only disprove something and tell, no, there is no functional dependency from B to C due to, oh, this contradiction. Okay, but you can't prove anything. At any time, some people come, add a record that ruins your dependency. And let's look at another example. We have a family tree, a child, father, mother, grandfather, and grandmother. And we store it. So in father and mother are possible to put in same record, but grandmother and grandfather in different, we have two pairs of grandmother and grandfather and didn't supply place to put them. So for Sophie, we have Alphonse and Sabine, and grandma of Lothar and Linda, and grandpa of Linda, and then another pair of grandma and grandpa. So we need to have two records. So if we look at this table, we can see that each time we have Sophie here, we have Alphonse here, and Sabine here. But different people, Sophie here and Lothar here, Sophie here and Hubert here, and the same with grandpa. They are changed. Grandpa here, Lothar and Hubert, and grandma is Lisa and Linda and Martha. So we can suppose that there is a functional dependency from child to father, from child and to mother. We can combine them in single. So every time, for if each child, father is single, is a unique value, and mother is unique value. That's right. And from state of the world, they may deduce this information not from the data, but we can deduce it from our knowledge of the world. But another thing that Sophie plus from combination of child and grandpa, grandma is unique. So every time Sophie and Lothar, Linda, only Linda. Sophie and Hubert, only Lisa. And Sophie and Lisa lead to only Hubert. So knowing child and granddad and grandmother uniquely identifies something. So functional dependency essentially is about unique identification. And left part is a key essentially. So left part is something that allows to uniquely identify something else. So that's an idea. So an analogy to functions are just common analogy that child has single father. So if we calculate a function for child, we'll have just single value every time. If we check Nicholas, Alphonse, Nicholas, Alphonse, Nicholas, Alphonse, every time we call function with the same argument, we have the same result. Every time we call function, another function for Nicholas, we have Sabine, Sabine, and Sabine, and Sabine. So only one mother. Every time we have record for Nicholas, and so on. And yes, so father and mother represents essentially two functions, and right side, this comma indicate multiple comma here independent multiple function, and comma there indicates Cartesian product. So for all the combinations, grandma is unique. So we'll call any combination, single column, pair of column, multiple columns, from the left side. We'll call such a column that has a dependency of the whole table, of the whole relation. Everything, any subset of column such that the whole relation depends on it, and the whole relation and the whole set of columns, called the super key. Anyway, R itself is a super key for itself, so equality is possible. Alpha may be just the whole R, but that's trivial, and we want to find something smaller. and we want to search for minimal dependency. And if we can find such an attribute, if we remove that attribute from alpha set, there's still be a dependency. So alpha without A, so beta still depends on alpha even without A. So if we may remove something from left part and dependency still holds, then it's not a minimal. So if nothing can be removed, so for every A from alpha, negation. So if we remove this from left part, that then it's not longer a dependency. If we can't remove anything from left part, then function is minimal. And in this case, if we find a minimal dependency, we'll call it key or candidate key. So minimal key is called a key or candidate key. So yes, yes, that's it. And we'll continue next time. Okay, so we'll continue next time.